guess we'll get the show going. Good morning, everyone. Welcome to the dealer conference. My name is Brian Teitelbaum. I'm one of the application engineers for AEE Solar. Been with this company for a while, and probably, hopefully help many of you in this room, and if not, I'd be glad to in the future. So we're going to do a little presentation on designing a battery-based system, both off-grid and on-grid battery backup. We only have 2 hours. That's a very short window of time to discuss a subject this big. So this is somewhat of a pared-down presentation, but I'll have to go through it fairly quickly. But I'd be glad to take any questions along the way. So feel free to raise your hand, ask a question, and we'll see if we can fit that in. But just try to keep it short so we can keep the pace moving. Just a little disclaimer here that AEE Solar is a distributor of goods and services, but we're not code-making experts and whatnot. The information we present is, to the best of our knowledge, accurate, but we can't make 100% guarantees on such things. So there are a whole bunch of different types of battery-based systems that are deployed using solar power or wind power or other things. Some systems are just directly powered either by the PV or wind. No batteries in them, no other controllers, no inverters or anything. Things like water pumps, fans, things like that can be done this way. They only run during the day when there's sunlight, if it's just a PV powered thing, or they only pump water when the wind is blowing, kind of thing. There's no storage. So it's only opportunistic and just uses power as it's available. Some systems are just straight DC, no inverters in them, but they do have batteries. These would be things like traffic control lights or street lights or billboard lighting, these kind of things. Weather stations and whatnot that can operate on 12 or 24 volt DC and can do so directly from a battery without having to use AC. Then there are many systems that the loads are AC only. That's the most common thing you're going to see for things like residential applications. Back in the old days, before inverters got good, most houses were dual wired AC and DC. So things like lighting and other essential things, communications and whatnot, were all done DC because it was much more reliable. AC was just used to run things like washing machines and stuff like that that were intermittent. And if the inverter broke, you weren't stranded. These days, inverters are really good, so we don't really do that anymore. It's certainly not worth the cost of dual wiring a house. When I built my off-grid house in 1990, I dual wired it and have since converted everything to AC, of course. It used to be that you could only get efficient lighting in DC, and that's certainly not true anymore. Then we have hybrid systems. We still do have hybrid systems with both AC and DC loads. You see these in like RVs, marine applications, boats, that kind of thing, where there's still some DC equipment. And then what we call hybrid systems, which what we mean by that is systems that derive energy from more than one source. So you might have PV, you might have a wind turbine, you might have a small micro hydro turbine, or an engine generator, but it's not just strictly on PV. Use a variety of charging sources for a battery. So we're going to go through kind of a little step-by-step here. And again, this is kind of truncated kind of thing, but the first thing is gathering information. When you want to design a battery system, whether it's for a residential house or some sort of industrial or commercial application, the first thing you do is gather information about the loads and the customer's needs before you can proceed. So obviously you have to figure out what your daily consumption is. And this is real different from doing grid tie. With grid tie, you're just looking at a yearly, generally with net metering, you're just looking at a yearly kilowatt hour consumption. And you just have to meet that. And so it doesn't really matter when you meet that. You could meet that in the summer and use it in the winter. It doesn't really matter. With battery systems and off-grid systems, you're really working more on a day-to-day basis because your loads are being run that day. You're making power either that day or within a few days, depending on the weather. So you have to find out how much energy the application will consume, whether it's seasonal. You might use more power in summer than the winter, or more power in the winter than the summer. You need to know these things. So for each load, you take the power draw by the hours used. So say it's a 1 kilowatt load and it's used for 4 hours. Well, that's 4 kilowatt hours of consumption. So I'll go through a little worksheet that we use. You can look up a lot of appliances on the Energy Star site. That's a very good resource for finding out actual usage. It's usually done as a yearly basis. You can divide by 365 to get it daily. Refrigerators, freezers, things like that are best calculated using those figures. So and then you have to look at peak load in watts, because your inverter has to be able to handle what the peak load is. You have multiple loads typically in a house that may operate at the same time, and your inverter has to be sized large enough to be able to handle those loads. And then you have to make some sort of guess of how many days of autonomy the system's going to need. And this is based on more on local weather conditions. So maybe you have 2 days or 3 days. It's fairly common to have cloudy weather before you get more sun. You need to have enough energy storage to be able to get you through those days. So you're going to need to make some sort of determination there, and that could be very wide. I mean, obviously, weather is completely variable. You might have 2 weeks of cloudy weather. That might be a rare occasion, or it might be a common occasion. You'll need to take that in mind depending on your local conditions. And don't neglect heavy snows. I say here, sometimes in the wintertime in some locations, snow could cover a PV array and essentially duplicate a cloudy day, even if it's sunny. So just be aware of if it's not possible to have somebody there to clear snow off, that might be an issue. And typically in off-grid systems, the sun hours are calculated, sun hours per day are calculated in the darkest month of the year, not the yearly average. See, with grid tie, we just go yearly average. It's a very simple thing because you can make a whole lot of power, like I said, in the summer, and you can bank all that credit, and then you can use it again in the wintertime. With off-grid, you can't store energy that long, and you don't have an unlimited amount of energy storage. A battery can only store a certain amount of energy. Once it's full, even if it's sunny out, you have no place to put that energy. It's not useful to you. So sun hours for off-grid systems are calculated on the sun hours per day in the darkest month of the year. It's typically December, but it might be January. If you're in places like, say, Indonesia, it might be June because they get a monsoon season. So, there are certainly variations in local climate. But this is a very important point to not just look at, peak sun hours on a yearly average, because that's not going to tell you a whole lot for an off-grid system. So there's a number of ways to analyze your loads that you're going to need to run. We do have a worksheet in our catalog. It's kind of a template. You can certainly develop your own, a spreadsheet of some sort, and list all the electrical appliances that you're going to use, down here, and then list the wattage of each one, and then how many hours. We calculate it on a week because, every day is different. You may not, for instance, wash a load of laundry every day, but if we do it on a week and then divide by 7, we get a daily average. So we'd have hours per week of operation, and this all adds up into a total watt hours per week. We have a step-by-step worksheet in the catalog for that, which could be real helpful. One thing to keep track of is what we call phantom loads. These are electrical loads for plugged-in appliances that are actually turned off but are still drawing some amount of power. Virtually anything that has a remote control, like a television, for instance, is actually internally on, waiting for the signal from the remote to actually show your picture. Now, it's in kind of a sleep mode where it's not using full power, but they still draw some power. And, normally it's like, a couple of watts. It doesn't really matter. But actually, when you go through a whole house, especially if you have a whole house with a lot of electronics in it, it can add up to a lot of power. This was a little chart from the California Energy Commission, of course they have dollar amounts there, which are kind of not meaningful. But, if you have a plugged-in computer, a wireless router, or an LCD TV, cell phone chargers, even a microwave oven that has a clock in it, right? These kind of things, they all take a little bit of power, and it can add up. In this particular example, that's 3 kilowatt hours a day, which is actually about my entire daily consumption of my off-grid house. But this is a much bigger house, many more appliances. So, just be aware of calculating something in there. A lot of this is going to be guesswork. You're not living there, you're not measuring the actual usage, you're doing some guesswork. But we have to start somewhere, and this exercise I'm going to go through about sizing a system, I want to emphasize that there is a lot of guesswork involved, and it's calculating to kind of the minimum. It doesn't necessarily mean that's your design point, but you need to know your floor to be able to effectively design a system that's going to work for your customers. So there's a bunch of choices to be made when you go to design the system and to apply the system. You're going to need batteries, at least for now. I mean, maybe someday we'll have hydrogen electrolyzers or some other form of energy storage, but I think for quite a while it's going to be batteries. Battery bank voltage, whether it's going to be, whether it's going to be 12 volt, 24 volt, or 48 volt. Virtually every residential system these days is 48 volt. 12 volt is still useful for really small systems, for specific applications. 24 volt kind of works well in some medium-sized systems. It might be a vacation cabin or something like that that doesn't have a lot of appliances, and 24 volt is still applicable. But generally, we're going to be working mostly in 48 volt systems. That's really become the standard in these things. And in the future, we may see high voltage battery systems. I'm sure you've all heard of the Tesla battery. It runs at 350 to 380 volts DC. Right now, there's no infrastructure to use those on an off-grid kind of environment, but obviously, the higher the voltage, the less amperage current you have, your wiring sizes could be a lot smaller, and everything is going to surge better and work better. But right now, we're working under 50 volts. It's kind of the code doesn't allow higher voltages in residential systems at the moment. And the type of charge controller. There are two different types of charge controllers. What we call PWM, which is pulse width modulation, and MPPT, maximum power point tracking. Pulse width modulation controllers are less expensive, they're more compact, they're generally in smaller sizes, although they do make them up to 60 amps at either 12, 24, or 48 volt. Essentially what a PWM controller does is it essentially just connects the PV array directly to the battery. There's no DC to DC conversion, no voltage amperage conversion in the controller. It's just really a direct connection to the battery. As the battery voltage rises up to preset points, it reaches a bulk setting, bulk voltage that can be programmed in usually or set with dip switches. And then at that point, the battery is getting more full. It takes less amps to keep it at that voltage. So the controller starts to do this high-speed on-off switching. And the amount of on time compared to off time is the pulse width. So the pulse width is going to modulate depending on battery voltage. As the battery voltage continues to climb and the battery absorbs more and more energy, it takes less amperage to keep that voltage at that high point. So it's going to be off more than on. So there's going to be a variation. But essentially, it's still doing a direct connection between the PV and the battery. So the voltage of the PV array has to essentially match the voltage of the battery. It's different from MPPT, where you might even have up to 600 volts DC on the array and charging a 48 volt battery, and it does a voltage conversion. But PWM is a much simpler controller, and that's why they're less expensive, of course, and more compact. They don't develop as much heat. They're actually very efficient, and are great for situations where it's a smaller kind of system and like say signage and that kind of thing works very well for that. But again, it does have low voltage limitations. Maximum power point controllers are more commonly used in larger systems. They maximize the energy harvest because you're actually operating the PV module or the PV array at its maximum power point voltage, so you get the maximum power out of the module. Whereas with PWM, you're really working on amperage. As soon as the PV module and the battery get connected, no matter what the voltage of the PV module or array is, it gets dragged down the battery voltage. So you might have, say, a 12 volt nominal PV module that has a peak power point of 17 volts. The battery's at 12 volts. As soon as those two connect, the PV module's going to be operating at 12 volts. So you're not getting the full power out of the module, essentially. You're getting amperage. The amperage is still full amperage. But because the voltage is lower, and voltage times amperage is watts, you're not actually getting the full wattage at that point. And as the battery voltage climbs, you're going to get closer to that power point and get a little more power out of it. But it's not 100% efficient, or 98% efficient at getting the wattage of the module out, whereas an MPPT controller can actually operate that module or that array at its peak power point voltage, and then it can convert that extra voltage into additional charging amps. So they do maximize the energy harvest. They have much wider input range. The voltage has to be above the battery voltage. So, you know, a 48-volt battery can charge up to about 60 volts. So your array has to be at least 60 volts and higher, and it will actually convert that extra voltage into more amperage. Generally available in higher capacity, these days up to 100 amps. They are more expensive. They're more complex. They're physically larger. They're heavier. So those are considerations to use. But in a situation where, you know, you're just doing a wall-mounted power system for, say, a house or something, then, you know, the size and weight is not a big issue there. They're certainly more expensive, but you do get much more power out of your system. Then you have to choose your module type. Most commercial modules these days are 60 cell. I'm sure you're all familiar with those, probably installed a lot of them. But you can still get 36 cell modules, which is what's called a 12 volt nominal module. It has roughly a 17 or 18 volt peak power point designed to charge a 12 volt battery effectively. And you can get 72 cell modules. These days, those are mostly used in large commercial applications, but that's being twice 36, that's essentially a 24 volt nominal module. It has a voltage range that matches very well with a 24 volt battery bank. 60 cell doesn't really, it has no nominal rating. It's not, wasn't designed as a battery charging module. It was designed as a string module to get into higher voltage, but they can certainly still be used with MPPT controllers to charge batteries. So if you're using the PWM controllers on a 12 volt system, you will need 36 cell modules. And if you're doing a 24 volt system, you could either use two 36 cell modules in series or use 72 cell modules. But if you're going to use 60 cell modules to charge batteries, you have to use MPPT controllers. And when I say have to, that's not quite true. But if you want to get the power out of the module, it's true. You know, so if you have, say, let's just say you have a module that has a peak power voltage of 60 volts, 30 volts, and an amperage, say 8 amps. It's roughly a 240 watt module. That 30 volts, if you hook that up to a 12 volt battery, it's going to drag it down to 12 volts. Now you're still going to get the 8 amps, but it's only going to be operating at 12 volts. Now as that battery charges, the voltage is going to go up a little bit. Let's say it goes up to 15 volts. Well, you have 15 volts at 8 amps. That's only 120 watts. So you're only getting half the power out of your module. It's still going to charge the battery, okay? So it's not like you can't use it, but you're paying twice as much per watt for your system there because you're only getting half the wattage. So that's why an MPPT controller, even though they're more expensive, is certainly cost effective. Again, just want to reiterate here that PV arrays for off-grid systems are always based on peak sun hours during the darkest month of the year. And we don't just say winter, because again, depending on where you are in the world, it may not be the winter. It is the darkest month, not the yearly average. But even with all this design, it's very, very hard to do a completely solar off-grid system. You know, usually it requires some form of backup power because the weather is just too unpredictable.
Do you have backup power on yours?
Yeah, I have a generator. And I had my system down basically to where I'd run my generator maybe 15 hours a year, you know, which is a really good design point. This past fall, we had about 6 weeks of solid rain where I am. So I had to run my generator a lot. I mean, it's just, you know, you have 3 kilowatt array out there and you're not getting much on a dark, cloudy day. So yeah, I mean, certainly you're going to need a backup generator. Adding some other charging source, a wind turbine, for instance. You know, small wind and grid tie systems is practically a dead industry. It's not cost effective. PV is so cheap that doing small wind turbines in a grid tie system is just not cost effective anymore. But they're very effective off-grid because very often when it's not sunny, it's windy. So at least you have something to charge with. It may not be as big a system as your PV array, but it can help keep your batteries up and extend your time. Micro hydroelectric is kind of a favorite of mine. The little hydro plants, a little Pelton wheel about so big. You need water that can come down a hill through a pipe and spin the thing, and it's got an alternator on it, similar to a car alternator. And that could run 24 hours a day, so that can be an excellent charging source, but very site-specific. Obviously rural area, mountainous area, where you can get water up a hill into a pipe, drop that down, use the gravity pressure to generate electricity. That works quite well. Maybe other forms of power out there, but generally a generator, and usually in off-grid systems it's going to be propane fueled. You can get diesels and things like that, but I generally don't recommend liquid fuels for off-grid customers. You really, bottled gas is really a better way to go. But you pretty much should figure on designing something like that in there. So when we're looking for peak sun hours, there's a number of ways to find that information. The good old NREL Red Book, which was 30 years of data from various points around the country, is one way to do it. You can get that online, or they actually print the book. As you can see down here, it's showing PV array at latitude or latitude plus or minus 15 degrees, or at 0 tilt or 90-degree tilt, and it gives you the monthly breakdown of both min max and the average peak sun hours for the, not only for the year at the end, but also for each month. So in this particular site, which is Honolulu, a fairly sunny site, at latitude, assuming you have an array at an angle equal to the latitude of the site, which in this case is 21.3 degrees. These are your monthly peak sun hour figures here. And it's showing December here at 4.8, January at 4.9. Those are both fairly dark. And not a huge amount of variation at this site. I mean, the peak here is looking 6.2. Many other sites in the US will have a lot more in the summer than the winter, so they have more of a gradation. But that's one place to find the information. Online calculator from PV Watts is an excellent resource to do. You can go to the NREL site and go to PV Watts calculator, and it'll show you the expected solar radiation in kilowatt hours per meter square, or peak sun hours for each month. It'll give you yearly totals here. And on this one, they're showing 4.72 as a December figure. We also, in the back of our catalog, if you have one there, we have maps of the world which have zones, and those maps are, again, based on the darkest month of the year. These are not yearly averages, so don't use these maps for grid tie. It's not going to be effective for grid tie. These are designed for off-grid systems. It's rough, it's obviously there's a lot of local microclimate in your site. A map of this kind of scale is not going to be 100% accurate, but they can be useful, especially if you're talking to customers overseas. You can do a quick look at where they are and see roughly what the darkest month average is. You will notice in this map here, there's a little spot in the United States right here. It says 7.0 out in the California desert. That's actually, if you look at all the maps, that's the highest value anywhere in the world. Even the Sahara Desert, the outback in Australia, other places. South Africa has a place at 6.8 or 6.9, I think, but this 7. I'm not sure exactly where that is. Probably the Carrizo Plain would be my guess.
Imperial Valley. It's over by Calexico.
Oh, is it? Yeah. Okay. There's just that dot on the map, and it's like, wow. At the darkest month of the year, they're getting 7 peak sun hours. That's a pretty amazing solar resource place. But as you can see from this map, actually the whole southwest of the United States is really excellent solar resource. But even other places in the country. I have had people up here in Seattle tell me that there's no way it's 1.5. So I'm not sure exactly how accurate this map is. It was actually developed by a company called SolarX, which was bought up by BP Solar, no longer exists. But it's still handy. All right, so pulse width modulated controllers. I'm just going to go through a little exercise on how you would calculate the size of the array for that. Yeah.
These are going to be available for us to email us, right?
Yes. Yeah, this presentation will be available to everybody. Yeah, there's a lot of detail in it, so yeah, it would be helpful to go through that. So what we do, when we're sizing with a PWM controller, we're sizing to amperage. You know, this is a little different than MPPT, which I'll go through next, which is done really wattage, because an MPPT controller is actually converting excess voltage into additional charging amps. It's really a wattage-based system. But with PWM controllers, you're really just dealing in amperage, because the battery voltage is going to vary, the solar array voltage is going to vary a little bit, but you're going to get that amperage calculation. So you need to just work on amps. It's actually a fairly simple calculation. We look at the daily amp hour consumption of the load. We multiply it by 1.2. We use a 1.2 factor as a charge-discharge efficiency cycle on batteries. You know, essentially, if you take 100 amp hours out of a battery, you need to charge it with about 120 amp hours of power, of current, to get it full again, because there's inefficiencies in the systems. Actually, batteries, when they're new, are more efficient than that. It's probably like, you know, they're more like 92% efficient. But as they age, their efficiency goes down. So we use a 1.2 figure, which is pretty conservative, and it's designed to accommodate some loss of battery capacity and charging efficiency over its lifespan. Because, you know, it might work perfectly on day one, 5 years later it's going to be a different story, you know, because the batteries are aging. So we look at daily consumption in amp hours, and batteries are rated in amp hours. That's essentially that it'll deliver a certain number of amps for a certain number of hours. They're typically rated on what's called a 20-hour rate. So a certain number of amps over a period of 20 hours will drain them completely. But we get our amp hour figures from our load calculations. Multiply that by 1.2, because you have to have more charging capacity. Divide that by your kilowatt hours per square meter per day, or your peak sun hours, and that tells you what your required array amperage is. So for instance, if you're consuming 100 amp hours, multiplied by 1.2, that's 120, and say you have 6 peak sun hours, then that's going to be a required array of 20 amps to do that. Then you need to select a module. You need to find the peak current rating, and this is the current at maximum power point, not the open circuit current, or the short circuit current rather. And you can usually find that on the module data sheet or on the back of the module, of course. Then you'll need to determine the number of parallel strings required. And here I have a little example over here. This is assuming essentially a 12 volt 36 cell module rated at 5 amps of current. So you put two in parallel, and you're going to have 10 amps at 12 volts. You can wire the same two modules in series for 24 volts, and it stays at 5 amps. You know, in parallel, the amperage is additive, and in series, the voltage is additive, as I show down here. You know, so determine the number of modules per string. If you're using 12 volt modules in a 12 volt system, it's just 1 module per string. 12 volt modules in a 24 volt system is 2 in a string in series, like this diagram down here. 24 volt modules, you can't really charge a 12 volt system, although like I said, you can, you're just going to get half power out of the modules. It's not really cost effective. So essentially it would just be 1 per string on a 24 volt. So to determine the total number of modules you'll need is the number of strings times the string length equals the total number of modules. Very simple calculation, really. You're just working on amperage. You could look at your amps and add them up, because you're generally picking modules that match the voltage of the battery. MPPT controllers are done more on wattage. And if you're using 60-cell modules, you pretty much need to use these if you're going to get any kind of full power out of the modules. Variety of companies make them. We're showing an Outback here, but Magnum has them and Midnight Solar has them. There's lots of MPPT charge controllers out there. They do convert the input voltage to the correct voltage for charging the battery. And the array voltage must be higher than the battery voltage. Now that's not 100% accurate. Essentially, obviously you need a higher voltage to be able to push energy into a lower voltage battery. So you have to have that gradient there. If the PV array goes off its peak power voltage, and which is lower than the battery, you'll still get some current flow. But what happens is you're operating that module higher up on the curve. If you look at a power curve for a module, as the voltage goes up, your amperage drops off really quickly until you get to open circuit voltage, in which case you have no amperage. But so if your array voltage is low, you may still get some charging, but it's going to be greatly reduced because you're going to be way up on the voltage curve of the module and not really using it effectively. So because we're based on wattage here, the controllers are rated in amps. So this is a FlexMax 80 over here from Outback. It's an 80 amp controller, but it's usable at different voltages. So, but depending on the voltage you have, you can put a certain amount of watts on there because, again, it's 80 amps, and it's rated at 80 amps of output, not input. You might only have 10 amps of input, but at a high voltage, and that's converting it into 80 amps of a lower voltage output for the battery. So as an example down here, 80 amps on a 48 volt battery system is actually 3,840 watts, but the same 80 amps at 24 volts is half the wattage. So you can only put half the size of the PV array on the same charge controller at that lower voltage, lower 24 voltage point. So this is one reason why 48 volt has become a standard in the industry. I mean, you have a $600 to $800 charge controller, and you would have to use twice as many of them for the same amount of power at a 24 volt system as you would in a 48 volt system. So 48 volt becomes a lot more cost effective at that point. Now, just as generally with a battery, I mean, a battery would have to be very dead to actually be at 48 volts charging at 80 amps. That's, probably wouldn't. So the voltage is going to come up to more like 50, 52. A 48 volt battery, if it's a flooded battery, goes between 59 and 60 volts. So, but it's still 80 amps. So you're going to, as the voltage rises, your actual wattage figure will change. So as a quick calculation, I usually use just 50, I use 50 volts for a 48 volt system or 25 volts for a 24 volt system. It's easy to calculate because 80 amps at 50 volts is roughly 4 kilowatts. So an 80 amp charge controller handles about 4 kilowatts of PV. You can push that somewhat depends on your weather. If it's a very hot climate, the array wattage is going to be lower because of the heat, so you might want to add a little bit on there. But it's a good idea not to try to push these controllers to their absolute limit all the time. They do build up a lot of heat, and of course heat lowers the lifespan and reliability of all electronics. So I generally, just rule of thumb, an 80 amp controller will handle roughly 2 kilowatts at 24 volts, roughly 4 kilowatts at 48 volts, roughly 1 kilowatt at 12 volts. So that's expensive controller to just have 1,000 watts of PV on there. And obviously you can use multiple controllers in parallel if you have larger systems than that. And it's true, PV array will rarely put out rated power except at high altitude sites. But if you're at 6,000 feet in Colorado and the snow on the ground and it's a clear day, yeah, you're going to see full output of that array, maybe more. There's a thing called edge of cloud effect, where when a cloud it covers the sun and the sun starts to peek out from the cloud, the edge of the cloud somehow concentrates that sunlight. You can see as much as 25% more power out of a PV array for several minutes on cloudy days that way. The controllers are current limited. It'll clip that off for the most part, so you don't really have to worry about that, but you will see that out of an array. You have to have overcurrent protection between the array and the controller. If there's a fault in the array, it's possible to backfeed battery current through the system all the way to the array, so you have to make sure that you don't want to start a fire, so make sure you have overcurrent protection there, and I'll go through those steps too. So string operating voltage has to be higher than the battery charging voltage. And again, with a 48 volt system, that gets up to about 60 volts. It has to be under what the limit of the controller is. Most charge controllers on the market now for this purpose have a voltage limit of about 150 volts DC. Typically, they stop working at 140 and it can actually be damaged over 150. So you don't want to push that too close, and you have to calculate that for your coldest morning, where your PV array is going to be at the highest voltage. So make sure you do that. The power, as I said earlier, the power will drop off dramatically if the charge point of the array falls below the battery voltage. You'll still operate. It'll just be way up on the power curve of the module. So your voltage will be higher, but your amperage will be greatly reduced at that point. And because a 48 volt battery charges at 56 volts or more, typically in these systems, they're using 60 cell modules. You have to use 3 modules in series. I know if you look at the spec sheets, a 60 cell module will have a peak power voltage of 30 to 31 volts, and wow, you think, oh, 2 of those, that's over 60 volts. That should be fine. In reality, it doesn't work too well doing that. There'll be a lot of times when that voltage will be too low, especially in hot weather, which I kind of calculated here. And on a really hot day, that 30 volt module is going to be operating closer to 27 volts. So 2 modules is only going to be 54. So again, it'll still charge up to 60 volts, but your charging current is going to be greatly reduced above the 54. So it's not going to be really effective. I don't recommend doing that. You could experiment on yourself doing that, but I wouldn't do that for a customer. So essentially, you need strings of 3 to charge a 48 volt battery effectively. 2 won't typically charge it to full power. 4 modules in most locations is going to exceed 150 volts on cold, clear mornings, so you can't really go with 4. It's kind of limited. You're really stuck with strings of 3 in series with 48 volt battery systems and charge controllers with a limit of 150 volts. At 24 volts, you could use 2 in series or 3. You can still use 3 as long as you don't exceed the 150 volts. The MPPT controller will convert that to the lower voltage of the battery. Gives you a little bit more leeway there. So one thing about 3s is now you're looking at arrays of 3, 6, 9, 12, 15, 18, 21. I mean, you have only certain numbers of modules you can do. You can't do 20 modules. That's not going to be divisible by 3. So just keep that in mind when you're designing battery systems that are DC based like this. Each string has to have circuit protection. It's just like grid tie. You're just using much shorter strings of 3 instead of 12 or 13 or 14 or 20 in a 1,000 volt system. So combiner boxes get used because you're going to have a lot more strings. As soon as you get over 2 strings, the code requires that you fuse each string. My recommendation, I think most of the manufacturers will say this, that even with 1 string, you need a fuse in a battery system because while the PV array is current limited, and that's, you can't, with a grid tie system with no batteries, you can't exceed the current in the array. So that's why you don't have to fuse 1 or 2 strings because you can't, unless you have a supernova of the sun, in which case you have a little bit more to worry about than your PV strings. You can't exceed that amperage. But in a battery system, you've got a battery sitting there, and even a small battery can deliver thousands of amps into a short circuit and melt wires very quickly. So it's very important to have circuit protection on all your wiring. So it's really recommended that even with 1 or 2 strings of modules in a battery system, that they be properly fused. Most modules have a 15 amp circuit rating. We're starting to see 20 or even 25 amp now as we're getting close to 300 watts on a 60 cell. We're starting to see more than 15 amps. So make sure you check that out with the module you're using. Typically, we use circuit breakers in these kind of systems. It's 150 volts DC. There are inexpensive circuit breakers available, generally through Midnight Solar or Outback. They're much more convenient than fuses. If they trip, you just turn them back on. You don't have to replace them, that kind of thing. And they're also cheaper, actually. But high voltage controllers generally still require fuses. There are some 600 volt DC circuit breakers out there. They're kind of limited in supply. They're pretty expensive. They're pretty bulky. We generally still use fuses in systems higher than 150 volts. Midnight Solar does have a line of 300 volt circuit breakers, essentially two 150s in series, and they got a UL listing for that. So you could do that up to 300 volts. Some charge controllers go to 200 or 250, but there are some. Schneider makes a 600 volt one. Morningstar Corporation makes a 600 volt charge controller, which you would just string as a normal, just like a grid tie, 600 volt grid tie inverter, but it's meant for battery charging. So you could use fuses in there. Again, all array circuits going to each charge controller must have a separate isolated feeder. As I said earlier, you can parallel multiple charge controllers, but each controller needs to be connected to its own array. You can't just wire a big array in with a single pair of output cables and going to a bank of controllers and have them share it, although we're starting to see that technology. It's starting to come out. Morningstar is working on a version of their TriStar MPPT controllers. We can put as many as 4 of them together on a single array. Midnight has their little 30 amp KID controller out. You could use 2 of those to create a 60 amp controller. So we are starting to see some controllers that can essentially, they can communicate with each other to the point where they can equally share the current from a single array. But generally with most of the higher power controllers, each controller needs its own array wiring, its own combiner box, overcurrent protection, that kind of thing. And then they're connected together on the battery side to charge a single battery. So you do end up with many more combiner boxes. Yes, sir.
Question, I've got a customer that's got a 24 modules feeding a 48 volt battery bank through 2 of the Outback 80 amp controllers.
Yeah, so 2 sets of 12 or?
Well, that's what I'm asking, because you can only put them, you say series, an array of 3, a string of 3.
Right.
And then but you can parallel arrays of 3 together?
Correct. You parallel strings of 3 together. Yes. So like with an 80 amp controller, generally, with typical 60 cell modules, you can go up to about 15 modules. You can maybe push it to 18 if it's a hot climate or something like that, but generally 15 modules on an 80 amp controller, which means 5 strings of 3. Okay, and that's one of the reasons why you have larger combiner boxes in battery or off-grid systems, is you need many more circuits in there. It's not just 1, 2, or 4 circuits for a grid tie system. You're really dealing with many more circuits there. But that's exactly right, as you would parallel strings of 3 to get the power. There's a lot of 60 amp controllers out there work great with 12 modules, so that would be 4 strings of 3 in that application. You can get combiner boxes that are separable into 2 separate circuits, so you just have 1 box and you can actually have 2 separate arrays coming into that box, and that can feed 2 charge controllers. That may or may not be convenient. I think in most applications, individual combiner boxes are really a better design point instead of running number 10 wire for longer distances in an array. We usually use separate combiners, but you can get some that are combined in there. Then on the charge controller circuit side, we also need disconnects and circuit protection between the PV array and the charge controller, and between the charge controller and the battery. The charge controller is considered a serviceable item. So like with any serviceable item, you need to be able to turn off all sources of power to it in order to be able to work on it. So in the case of a charge controller, you have power coming from a PV array into the controller. You also have potential power coming from the battery to the controller. So you need disconnects and over-circuit protection on both sides of the charge controller. Again, typically, circuit breakers are typically used in these systems, at least in the 150 volt range. The input breaker for the PV array has to be sized at 156% of the short circuit current of the array. This is a factor of 125% twice. It's a code requirement. Essentially means that, except in a fault from backfed battery current, that circuit breaker will never trip. You know, it's kind of an odd quirk of the code, is that they're telling you to put in a circuit breaker on a current limited PV module or array and design it in a way that it would never trip. But it is really just there for fault currents from the battery more than it is from the PV array. Although if you have multiple strings combined into it, you could get current into a fault in a single module.
Does that mean you'd have to then upsize your wire in that situation?
Well, I mean, typically what you would have is a string of 3 modules, and that's usually on a 15 amp fuse, so really you're fine with number 10 wire or even number 12 wire. Once they're combined in the combiner box, the output of that has to be a much larger wire, has to be able to handle the combined current. So for instance, if you did have 5 strings of 3, and say it was well, you have to calculate it on the short circuit current, so let's say it was a 10 amp module, you could have 50 amps going through that line there. So with 50 amps, you're going to need to use a number 6 wire just for ampacity reasons. And then you actually have to calculate the circuit protection based on 156% of the short circuit. So it's really going to be more like 75 amps, 77 amps, or whatever that turns out to be. So actually now you're talking number 4 wire, or maybe even number 2. And then if you have to go any kind of distance, you have to worry about voltage drop for distance. So you have to calculate that based on there, which by the way, in the catalog, we have some charts in the back of voltage drop, wire calculations that are based on a 2% loss. You know, we try to keep our losses from the array to the battery at 2% in the main transmission. So yeah, there's a lot of factors in there, but yes, you are going up in size essentially. Very, very often with say an 80 amp charge controller, you'll use a 70 or an 80 amp input breaker. You know, that's fairly common. Now the output of the charge controller is going to be at 80 amps. There are some circuit breakers that are rated for 100% duty cycle. I don't recommend doing that. I don't think any circuit breaker should be operated at its 100% peak. You know, there should be some leeway there. So generally with an 80 amp charge controller, you'd probably use a 100 amp breaker on the output, on the battery side of the charge controller. Because at that point, you don't need the 156%, you just need a 125 factor, just like all circuit breakers. So yeah, so you typically would have an 80 amp input breaker into an 80 amp charge controller, 100 amp output breaker on an 80 amp charge controller. Would be fairly typical. You do have to make sure that the input breaker doesn't exceed the maximum input amperage rating of the charge controller. It's usually not a problem, you know, but you might want to look at the specs of the charge controller and make sure that you don't have more amperage coming into it than it's rated for. Wire between the breaker and the combiner box must meet or exceed the current rating of the breaker used. That's fairly obvious. Or if you're using even a 20 amp circuit breaker, you could use 12 gauge wire. You probably want to use 10 just for voltage drop, but you could certainly use a 12 gauge wire. The charge controller breaker also acts as a disconnect. It serves as a battery breaker on the battery side of the charge controller. Again, you know, I just mentioned this. If it matches the charge controller output rating, it has to be rated for continuous duty to get 100%. And some manufacturers, you know, size like that. I'm generally not a big fan of that. I'm just not a big fan of pushing electronic components at 100% of its duty cycle. I just don't think that's a really good design point. With the exception being grid tie inverters. Grid tie inverters, you get a 5 kilowatt inverter. It's designed to operate at 5 kilowatts. I mean, it's designed. Dealing with battery systems, you're dealing with more variable, more flexible voltages and amperages. Ambient temperature is a bigger thing. They generally have cooling fans. It's really best, and especially with circuit breakers and things, to not really push it to its absolute limit. And leave yourself a little leeway there. You may save a little bit of money and then have some nuisance tripping that's going to wipe out all that. You get your customer calling up, my system's not working because the circuit breaker tripped. It just got hot and tripped, or something like that. It's really best to size it a little higher. Obviously, if it's not rated for continuous duty, you have to rate it at 125% according to code. In Outback systems, they have an assembly that is not only the output breaker or the battery breaker for the charge controller, also acts as a ground fault disconnection device. Some companies build that into the charge controller, some have it upstream on the PV side of the charge controller, some have it on the battery side, like what Outback does. There's a variety of ways to do it, and generally it's best to follow the manufacturer's recommendation for the system you're using. But again, if the charge controller is operating near its limit, it's a good idea to oversize that battery breaker to avoid nuisance tripping. You really don't want the system shutting down when it doesn't need to. And obviously, if you have a larger circuit breaker, your wiring has to be larger too to handle the ampacity. So if you're using, for instance, a 100 amp breaker, you're pretty much going to need number 2 wire to do that. Otherwise, number 4 wires it doesn't have an ampacity of 100 amps continuous. So generally it's number 2 wire at that point. Ground fault detection is required in every system, has been for a number of years. Again, sometimes it's built into the charge controller, sometimes it's actually a circuit breaker based design. We call them GFPs or GFDIs. They come as an assembly, and a number of companies make them. The Midnight Classic controllers have it built in. The Schneider controllers have it built in. Midnight controllers and some others, Morningstar, for instance, use an external device. It is a connection between the DC negative and the ground, and that's where the bond is, generally through a resistor. It's kind of a high impedance bonding, but it still is code compliant for that. Traditionally installed between the array and the charge controller, but again, it can be on the other side of the charge controller. Now, the 2011 code also requires arc fault detection in PV arrays. Currently, there are no UL-listed arc fault detection devices that are available separately. The new Magnum 100 amp controller and the Midnight Solar Classic controllers have arc fault systems built into the controller that apparently work quite well, but they're not UL listed for that. So they haven't been able to get them listed. So far, we're having, inspectors are waiving this requirement because there's no device on the market for it, but it's going to keep coming up, and it's going to be pretty much required. I suspect that the arc fault detection is either going to be built into the charge controller as just a feature that you won't have to deal with separately, or it's going to be in combiner boxes, which is actually a better place for it, because the most likely place for the arc fault is going to be, in the external wiring of the PV array. So being built into combiner boxes seems to make a lot of sense to me, along with the rapid shutdown gear, which is also coming, which I don't talk about much in this presentation, but that's another thing that the code is requiring, is that, especially if PV modules are mounted on the roof of a house, that you have to be able to disable the output of that within 10 feet of the array. So these are things that are coming into these systems and making them more complex and more expensive for us, but also safer. So it's a good thing. But right now, they're just, if you get an inspector talking about arc fault, well, you can tell them you can install a Midnight Classic charge controller, but it's still not a UL-listed device under the UL test for arc fault, so I'm not sure that's going to compete. So usually you get a waiver. It hasn't been a problem so far. The inspectors in Colorado are particularly tough. We usually have to argue back and forth with them for a while, but because there's no identifiable device to actually meet the code, you can get a waiver for that, luckily. Okay, I'm going to talk a little bit about batteries, because that's kind of the heart of the system here. There's lots of different types of batteries. Okay, we're about halfway through. I'm going to start with flooded cells. Flooded cells have been the most common batteries to use in off-grid systems for many, many years, decades. And mainly because sealed batteries haven't been all that good up until maybe the past 10 years. So they were been the most common. They are generally the most economical in terms of life cycle, in terms of capacity, and that kind of thing. They're usually more economical. They have excellent cycle life. You get deep cycle batteries. They can have very excellent cycle life. Electrolyte loss is replaceable. So if they charge hard, and you lose water. I mean, essentially the water is broken down to hydrogen and oxygen and escapes as a gas, and that is replaceable. So they can handle overcharging. If say a charge controller fails and just happens to overcharge the battery, well, it doesn't kill the battery. You just have to add some water to it, assuming you catch it in time. However, because they're not sealed, they have to be upright, can't be mounted on their side. You can't ship them in UPS or air shipment. They're hazardous material. They require isolation, usually a battery box container or some sort of enclosure, and has to be well vented, because when batteries are under charge, they emit hydrogen and oxygen gas, an explosive mixture, and also hydrogen sulfide gas, which is poisonous. It's that rotten egg smell. It's actually poisonous. It requires maintenance. Water must be added. Should be at least checked monthly. Usually when the batteries are fairly new, you don't have to add water monthly, but they should be checked. They require regular equalizing charge, and what that is over time. I mean, typically you have a bunch of cells. A lead acid battery, a cell is an energy producing unit in the battery is 2 volts. It's always 2 volts. It could be the size of a little battery, or it could be the size of this room. If it's a battery cell, it's 2 volts. And what you do in a case is they have several cells in there to get higher voltage. And you can tell by the number of caps on the battery here. So like this battery shown on the side here has 2 of these yellow caps. That's a 4-volt battery. So you would wire a bunch of those in series to get up to the 48 volts. And so you have all these different cells, and every cell operates a little differently. It's manufactured a little differently. You get little variations over time in their voltage and their capacity. So every once in a while, you have to essentially overcharge them, and that brings the lowest cells up to the higher level of the higher cells and keeps all the cells equal. There's also what happens with flooded batteries. It's a liquid electrolyte, generally sulfuric acid, and the sulfuric acid and water is mixed, but the sulfuric acid is heavier than the water. So in a stationary battery, over time, the acid will settle out of the water. You'll get a higher concentration of acid at the bottom of the battery inside, and higher concentration of water at the top. It's not a problem in your car battery because you're bouncing down the road all the time. It's always mixing it up. In a stationary battery just sitting there on the floor, you get this stratification effect, especially with tall batteries such as these industrials here. It gets a problem. So on somewhat regular basis, at least twice a year, probably best 3 or 4 times a year, we do what's called equalized charge, which means we fill the battery up completely and then continue to charge for 2 to 4 hours at a higher voltage. 48-volt battery will typically go up to 61 volts, even 62 volts. What happens there is the battery will bubble quite heavily, and that bubbling action will stir up the electrolyte and keep the electrolyte from stratifying. Because when you get a higher concentration of acid at the bottom of the battery, it's going to corrode the battery plates at the bottom of the battery and greatly reduce the lifespan of the battery. So it's important to keep that mixed up. Of course, it takes energy to do that, and that's energy that's actually not being stored. You're just using it to split water and cause bubbles. So it's not, there's some efficiency loss there. In the wintertime, if there's not a whole lot of sun, you probably have to do that by running a generator. In the summertime, batteries might be full by 11 a.m. You can just, essentially, you can program the charge controller to defeat the set points and equalize off a PV array. But it's still energy that you have to produce that's just used for battery maintenance. It's not actually used to run loads. So there is an efficiency loss there.
How often do you need to do that?
It depends on the age of the battery. New batteries should be done at least twice a year. 4 times a year is probably better. Anytime a battery is left in a partial state of charge for, say, more than a week, it should probably be equalized. What happens when you discharge a battery, a lead acid battery, is you build up lead sulfate. That you have lead and sulfuric acid. The reaction component of that is lead sulfate, which forms a crystalline structure on the battery plates. The longer that crystal exists, the harder it gets. So you can't redissolve it over time. So if a battery is left in a partial state of charge for a week or 2 weeks, those crystals will be forming on the surface of those battery plates. You want to redissolve those. So an equalizing charge will help to do that by boosting the voltage up and getting the electrolyte mixed. Yes, sir.
What are considered higher temperatures? What range is?
Well, batteries are rated at 77 degrees Fahrenheit, 25 degrees C, and their lifespan is calculated based on that. At lower temperatures, they just have less capacity, but it doesn't affect their lifespan. Batteries are called storage devices. That's kind of a misnomer. What a battery is actually an energy production device. It's a chemical reaction that produces an electrical current. That's a reversible reaction. You can put electrical current to it, reverses the chemical process back to its thing. But it's actually producing the energy through the chemical process. So you want to be able to reverse that thing. Now, at higher temperatures, the chemical reaction is so more aggressive that it actually will chew up the battery plate. So a battery that's continually operated at, say, 100 degrees Fahrenheit, it might only have a third of its normal lifespan. It's greatly reduced lifespan in higher temperatures. So anything above maybe 80, 85 degrees is really starting to reduce the lifespan of your batteries there. Yes, sir?
Can you equalize too often?
Yeah, you can. Continually overcharging a battery tends to break down the positive plate. And you'll start looking in the battery, you'll see all this kind of red dust settling on all the components of the battery. That's a sign of overcharging. So yeah, you can equalize too often or overcharge too often. That's the whole reason we have charge controllers, is to prevent the battery from being overcharged on a regular basis, essentially. So you don't want to do it too often and be too aggressive with it. As the batteries age, they should be equalized more often, because you're going to have just a lower efficiency charge rate. You're going to have sulfate crystals built up in there. So yeah, in situations, in hot climates, might want to look at a different technology. A lot of places that have big battery systems in hot climates put air conditioning in the battery room. Of course, now you're adding a load. It's kind of a funny thing, is you're trying to preserve your batteries, and here you're adding a fairly major load to your batteries just to keep them cool. But it works out to be pretty cost effective, actually, especially if you have a large system with industrial batteries. Are very expensive. Obviously, adding the load, you have to go back to your load calculation, add that into your PV array to make sure you're making that energy back to make up for that air conditioning setup. By the way, lithium batteries also don't like high heat, so they take a little more heat. They're not as degraded as much, but they also don't work quite as well in high heat. We say here sensitive to shock and vibration. Yeah, that's somewhat true. Essentially, you have lead plates hanging from the top, and they're, even though deep cycle batteries are meant to be stationary. Obviously your car battery gets a lot of shock and vibration. It's the same kind of technology, but it is designed a little different to handle that. Then we get into gel cells, which are jelly. Instead of having a liquid electrolyte, it's bound up in kind of a jelly or a gel form. These work very well for stationary applications in high cycle applications, like street lighting systems and sign lighting systems and standalone data monitoring, weather stations, these kind of things. They actually have very good cycle life, very high efficiency. They have very low self-discharge rate. They require very low float current to maintain their voltage. They're very shock and vibration resistant. However, if you overcharge them, you're going to gas them. That gas is going to escape, and there's no way to put it back in. So overcharging any kind of sealed battery can really shorten their life. Don't handle high temperatures real well, because they just have no way of losing fluid, mostly. They do cost more than AGM batteries, but generally have much better cycle life than AGMs and kind of deep cycle applications. They're not available in very big sizes, but they are available in these smaller kind of sizes here. I've seen them as large as L16 batteries, but they're the batteries I generally recommend for small standalone systems like billboard lighting and that kind of thing, boat dock lighting, that kind of thing. They seem to last a lot longer than the AGM batteries do. But AGMs are really more common. They are really the battery to use these days for backup systems, and now we're really getting to the point where we're starting to see cycle life of sealed AGM batteries pretty close to flooded batteries. Some of the better AGM batteries will get 1,800, 2,000 cycle ratings, that kind of thing. Flooded batteries might be more like 3,000 cycles, 2,800 or 3,000 cycles, but still the AGMs are coming on pretty good as having really good cycle life. They're sealed, which is really nice. You still have to vent them just in case they do accidentally release gases. If there's a failure of some sort and they're overcharged, they will release some gases. They have a little valve on them. VRLA is valve regulated lead acid. They're actually under pressure. There's about 3 pounds of pressure inside these batteries. And if the pressure increases because they're overcharged, it will release some gases, and that you can't put anything back in, so you have lost capacity at that point. So they are sensitive to overcharging. It's very important to have good charge controllers on there. Charge controllers should have temperature compensation because the batteries are going to take different voltages depending on different temperatures. All the better charge controllers do. They are high efficiency. They're very shock resistant. You can often ship them without a problem, although not all of them. You have to check on a particular battery to see if they're shippable. Yes, sir?
What would you define as overcharging?
Getting over its rated voltage. So a typical, say, a 12-volt AGM battery would have what they call a peak voltage charge point of like either 4.2 or 14.2 or 14.4 volts. If you get over that, of course, you can temperature compensate that. When a battery's cold, it can take slightly higher voltages. But if you get over that, then it just starts to break down the materials in there into gases. It essentially it has internal gassing, and that can escape, and you can lose the material. So you need very good charge regulation to make sure you don't get over those voltages in sealed batteries. It's really true with flooded batteries too. It's just with flooded batteries, you can put more water in them so that they're not instantly damaged by that. But with sealed batteries, you will lose materials. They work very well in high power applications. They have very high discharge rates. You can get them in pretty big sizes. I think GNB Absolite, one of the higher quality industrial batteries, they make up to a 6,000 amp hour cell, single cell, and you can put those together so you can get very large capacities. You can do that with flooded batteries too, but they're not as common, a lot harder to handle. Again, reduced life at higher temperatures like all lead acid batteries. Electrolyte can't be replaced. The initial cost, especially in the smaller sizes, is higher than flooded batteries. Yes, sir. Oh, yes, sir.
Are the AGMs less temperature sensitive than the lead acid? Or?
No, I wouldn't say so. It's pretty much the same. Yeah, I mean, it's really the same technology. It's lead and sulfuric acid. It's just combined in a different form in the battery, but the chemistry is really pretty much the same. There's some slight differences. Some batteries use a little bit of calcium in the grid to hold it together. Some use antimony. The flooded batteries are more likely antimony in there, and the sealed batteries are more commonly calcium, although they go back and forth. And they have slightly different charge-discharge profiles and that kind of thing. But really, it's basically the same technology, the same chemistry involved. This is kind of a new development. A couple of companies have come out with AGM, which, by the way, AGM is absorbed glass mat. Essentially, instead of having a liquid in there, they have a fiberglass matting that absorbs the electrolyte, and that's wrapped in the plates. So it's what they call an immobilized electrolyte. But by adding some nanocarbon or carbon particles into the mix, this is somewhat new technology, they figured out that that has some advantages in the battery. Usually added to the negative plate, improves the partial state of charge performance. What it's doing is it's preventing the formation of those sulfide crystals. It's interfering essentially with the formation of the crystals. So you get much less solvation on the negative plate, which means that the battery can handle longer periods of partial states of charge without damage. It also has less self-discharge rate into it. This is kind of an excellent new technology. I mean, the thing is, Outback has one out in a sealed version, AGM. Trojan has their smart carbon flooded commercial industrial batteries. They've just come out in the past year or two. We haven't seen over time, what kind of improvement this is, but it looks very promising. So yeah, it's certainly something to look at. And one big advantage is you could be at a partial state of charge and not build up the sulfate, which means you can run for longer periods of time in a partial state of charge without actually damaging the capacity of the battery. So you can cycle them more in the mid part of the battery without having to fill them up as often. That 44% is a manufacturer's claim. Again, this hasn't been proven over time by third-party people, and like I always say with new products, the manufacturer speaks very highly of it, but but you can take that not very far. We really need to see over time how this works out, but it does look pretty promising improvement in battery technology, which lead-acid batteries have been around since before Thomas Edison. I mean, and they haven't changed much. There's been some improvements, certainly improvements in manufacturing process, but not a whole lot of improvement in performance. But this is kind of a major breakthrough. There's also some companies that are working on some other what they call ultra batteries, which have not only lead plates and lead oxide plates, but have carbon plates in them. And they're kind of like a hybrid between a lead-acid battery and a supercapacitor. So they can store and dump huge amounts of energy very quickly, but they also have very long cycle life. It's very promising technology. There's a company that's working with them in Australia. They have them on the market. There's nothing on the market in the U.S. yet, but several manufacturers are working on that. But we do have these carbon-added batteries. They're pretty intriguing. I'm probably going to put a set in my off-grid house to see how long they last. Then I can recommend them. So it's somewhat of an experiment. It doesn't seem to have any detriment to the system. So, but they are running, about 15% higher in cost. They're saying a 44% improvement in cycle life with a 15% higher cost. That's a pretty good deal. But again, it's a little unproven, but the chemistry is pretty sound. So we're pretty excited about this development.
And how do you think these ones? So are heat a factor in these ones?
Yeah, heat is still a factor. Yeah.
So because heat, all the batteries, heat seems to be a big factor.
Yeah.
And so like we're in the desert, so we do we do Palm Springs and where we live.
It's hot. Yeah, even in a garage. Yeah, right. Yeah.
So if you're building a system that needs to last and you need to warranty it, what are you going to use?
Well, in a hot climate like that, you pretty much need to have them in a conditioned space. You'd probably have to have an air-conditioned space. My sister-in-law's father had a place in Palm Springs, and he would park his Mercedes in the garage, in the summertime, and then spend time with, in Northern California with the family, and then come back, and even though the car was in the garage, all the rubber would be ruined. You know, just parked in the garage, you know? So he had to put an air conditioner in the garage just for the car, which is kind of silly, but you know, when it's 120 degrees outside or 115 degrees outside, it gets pretty hot in the garage, so that's an issue.
And if you're not gonna do that, or if the customer doesn't wanna do that, or just decide to do it, would you just go with lead acid?
Yeah, probably would. Insulation could help, you know. You can get, you know, like say traffic signal boxes, you know, you're running a traffic signal on a battery system or say railroad signal, something more off-grid. You can get exterior battery boxes that are insulated. And the thing about the insulation is you know, normally with insulation you're keeping heat in, you know, because you have a heat source that you're keeping in. In this case, you're keeping heat out. Batteries are very heavy and very dense. It takes a long time for them to absorb the heat. So assuming it cools down in the evening, an insulated enclosure could be very effective to keep the heat of the day from actually heating up the battery, and then at night it can be, you know, more cool. But if it's still hot at night, you're just going to have a problem. You might have to calculate that you might only get half battery life, for instance. I mean, that just might be the thing you end up with, you know, kind of thing. You might, I'll go through some other battery technology here, but the Aqueon batteries might be an interesting choice in your situation. Very hot climate, right here, as a matter of fact. This is a whole new technology that's just been coming on the past couple of years. They're here, they have a booth in the expo. Aqueous hybrid, it's essentially a saltwater battery. No acid, it's just salt water. It's you know, sodium ion exchange, essentially. They're claiming up to 3,000 cycles at 100% depth of discharge, 6,000 cycles at 50%. That's probably twice what a lead acid battery does. And actually, what I find with off-grid systems, even with lead acid batteries, is if they're properly cared for, they'll last longer in years than the cycles would indicate. I mean, normally, if you say, oh, gee, it's going to cycle every day, that's 365 cycles a year. You know, in 10 years, that's 3,600 cycles. Well, in reality, you're not cycling it every day, or as deeply every day. It kind of goes up and down, and batteries tend to last longer than just, you know, counting each day as a cycle. So this could be a very long-lasting battery pack. I've seen some high-end industrial flooded regular lead acid batteries last for 20 years in off-grid applications. So this might even be longer than that. No toxic materials, very durable, can handle higher temperatures, won't explode, has no thermal runaway issues, it doesn't support a flame. It's actually the only battery so far that's passed the UL test for flame issues, or explosion issues. All non-toxic materials can be just thrown in the trash or recycled, essentially, afterwards. Operates up to 40 degrees C with full lifespan, so that's 113 degrees Fahrenheit. You know, so this might be a choice. They are now running about 2 to 3 times the price of lead acid batteries. Now, if it lasts twice as long and costs twice as much, you've broken even. So that's not a big deal, you know. So it might be a little bit more expensive. It's big, physically large. It's physically heavy. That little stack here is that's right. So it might be cost effective. So yeah, there may be a higher upfront cost, but over time you're actually saving money on the deal. Plus you're not having to deal with it every few years, you know. Yeah. So this is a very interesting technology. This little picture here is maybe a little deceiving. That's like a pallet. You know, it's big. And it's 3,000 pounds, right? And it's about, you know, roughly about 500 amp hours. It's heavy. It's big. It is modular, so you can move it in sections. You don't have to have a forklift necessarily. Would be a bunch of those. It would be 3 or 4 of those kind of things, which takes up a lot of space. You need a really strong floor. Yeah, it's very interesting. It has some limitations. Well, if you look at this picture, and like I say, you could talk to them too. They have what they call a stack. this is called a module, which is a whole assembled unit. It's assembled out of stacks. Each one of these vertical stacks here is 48 volt. So in this particular one, it's a 3 times 4. There's 12 of them in here, 12 48 volt stacks. Each one is about 50 amp hours of rated capacity, 48 volts. They're talking about doing a 24 volt one that's half as high. Yeah, they have one stack over in the showroom here. You know, they don't have the whole module like this. It does have a fairly low rate of charge and discharge. As a matter of fact, I understand with this unit here, well, with the stack, if you take a stack and you short circuit it, you get about 100 amps. You know, so that's, you know, if you did that with a similar size lead acid battery, you'd have about 3,000 amps. You know, so yeah, it's limited, a little limited on its surge or its ability to take a charge, but what you do is you just put more of them in parallel. You know, so if you had 2 of them, that's 200 amps, and 3 of them is 300 amps. I mean, you could certainly add it up to do that. But again, it is going to take up more space, not nearly as compact. Although if you talk to them, it's like, well, for the cycle life and the amp hours, it's about the same amount of floor space, but they're tall, so you know it is taking up more physical space. Limited capacity at higher rates of charge and discharge. You just need a bigger system. It's very interesting, and actually we've been working with these guys for about 3 years now, and you know, kind of back and forth, helping them develop it. It's U.S. manufacturer, and they're on the 3rd generation now, and huge improvements over the 1st generation in terms of capacity. I think so, yeah. Well, they claim that, you know. I mean, it does have a little lithium in it and a few other things, but it's sodium, you know. If you're on a low sodium diet, you don't want to eat the thing. But essentially what he says is that, you know, as it ages, you know, towards the end of its lifespan, and it has a fairly, you know, even amount of performance, and then towards the end, it just drops off really fast. And he said the internal components basically dissolve into mud, just this mud thing. And then there's plastic cases, and there's some aluminum, some steel in it that can be recycled. But the mud you can just scoop out and just dispose of it normally. It's not toxic waste. It's kind of nice. Yes, sir. I asked him that, whether you could like just use the plastic cases and the metal components and just refresh it. And he said, no, there really wasn't a way to do that because they are sealed. You know, when they manufacture it, you know, they seal each section. So. Unfortunately, no. Yeah, I thought that was kind of cool too. You could just get your refill bag of mud essentially, and salt and water, and put it in there. But no, apparently it's not quite that simple. But still, you know, it's very interesting technology. We're actually setting up a test bench that we're going to do online monitoring with this battery and see how it works over time, because it's a whole different concept. You know, it's. All the hype is going to lithium ion, and lithium ion is wonderful for automobiles. Not necessarily the best choice for stationary. I think that's a battle that it has to yet win, and these guys are going to be big competitors, I think, in that battle. There's other technologies going on too, of course. Speaking of lithium, you know, the Tesla Powerwall, which we're hoping to market as soon as we really have all the infrastructure together to be able to use the thing. It's, you know, pretty exciting technology. One of the most exciting things for me is it's a high voltage system. It operates between 350 and 380 volts DC. You know, one of the things we're seeing now with a lot of off-grid systems is, you know, really large off-grid systems. You know, when I started installing off-grid PV systems back in the 1980s, first of all, a high-power PV module was maybe 50 watts. When the 75 watters came out, it was like, ooh, wow, high power. And if you put 1 or 2 of those on somebody's off-grid house, it changed their life because they weren't running kerosene lamps anymore. They could have electric lights. I mean, this was a big thing, you know, to just have 1 or 2 75-watt modules. Now I get asked all the time to design off-grid power systems, you know, 20, 30 kilowatts. It's like, you know, it happens, you know, big houses, you know, huge air conditioning loads, swimming pools, hot tubs, the whole thing, you know, multiple refrigerators and freezers, and, you know, yeah, it's kind of crazy. I ran my off-grid house for, you know, probably 15 years on 400 watts of solar, and my wife and I were quite comfortable. But in order to do that, you have to cheat. Our refrigerator operated on propane gas instead of electricity. We used the laundromat in town, that kind of thing, you know. But, you know, microwave, vacuum cleaner, stereo, TVs, computers, you know, none of that's a problem to do that. So, I mean, you can certainly be much more cost effective. But yeah, we certainly see bigger systems. Tesla right now is really marketing to, you know, the average urban or suburban market. I mean, they're not really looking at off-grid. It's not really particularly in their sphere of influence. I've talked to them about it. They have an industrial battery product that's rated 100 kilowatt hours of storage. It's a big, I don't know, it's probably about 3 foot square, stack 8 feet high, designed to be mounted outside on a concrete pad. It's only available now to utility scale at 500 kilowatt hour chunks, because they have to have active battery management, and only does it in 500 kilowatt hour chunks. But this little unit that that they've released on the world, at least the hype, they're going to have 2 units. One's going to be rated at 7 kilowatt hours and one at 10. The 7 kilowatt hour one is meant for virtually daily use and mostly peak load shaving and that kind of thing. It's not really designed for backup power, although you can theoretically put multiple units together and have enough for backup. They're actually calling it a 6.4 or 9.1 kilowatt hour, either a daily or a weekly version. I'm sure it's going to sell. You know, it's going to break the ice of having battery systems distributed among residential houses and small businesses, and ultimately is going to lead to kind of more of a smart grid kind of arrangement where you can use more of your power on site. You can shave peak loads off and not get demand charges from utility and that kind of thing. It's going to be fairly useful for that. Well, actually, I understand that they are shipping some into the Northeast. They have some test systems up. You know, Tesla owns Solar City, so they're working with Solar City on some applications. It's really just kind of beta testing at this point. Yeah, I think so. They're working with Solar Edge. Solar Edge has the inverter technology that more closely matches their power curve. Yes, sir. Right. Right, that's right, yeah. It is, the whole concept is really kind of changing how we design these whole things, you know, because of the higher voltage. Now, the reason Solar Edge works so well with Tesla, and I'm not sure if it was a coincidence or not, but the way Solar Edge works, if you're familiar with the Solar Edge grid tie system, is they use optimizers on each module and essentially creates a 380 volt DC bus between the modules. You know, instead of having just additive voltages of a string, it really is creating, through DC to DC conversion, it's creating a bus. It's roughly 380 volts DC. Just happens to be right in the voltage curve of this battery. So essentially you can plug the battery in just like another PV string, you know, and their inverters are being designed with multiple inputs in the control for that. So it matches right up to the same voltage of the modules and can act as a bidirectional power source or absorption, essentially. Yes, sir.
You know the approximate dimensions?
Well, I've seen it. It's about that wide and about maybe that tall, and it's designed to be wall mounted. About 8 inches deep, and it's going to come in designer colors. You can get red and blue and green and all this stuff. And as a matter of fact, I had a little fun with the Tesla text. We were showing it at the Intersolar show in San Francisco. We had it in our booth, and I'm looking at the conduit hookups, you know, and it was a mock-up, so it wasn't really a real thing, but it has a flat area on the bottom that you could have conduit hookups. And I said, well, you know, designer colors, you know, how are you going to do the conduit? He says, well, they really want the conduit in the back through the wall so you don't see it. It doesn't mess up the look of it, you know. And I said, well, that's going to work in some situations, but in some walls and whatnot, you're not going to be able to do that. You're going to need surface conduit. And he said, oh, no problem. We have this area in the bottom you can, you know, knock out for, you know, do conduit punches and knock it out. I was looking at it and I was going, well, it's going to come in designer colors. Are you going to have designer colored conduit fittings?
And, the technician got this horrid look on his face. He says, "Don't tell Elon that." But, yeah, right, but they probably will. You'll probably get, you know, LBs and LLs and conduit fittings and, you know, designer colors. In response to this, Mercedes just came out with their home battery. I don't know if they're having plans on marketing it here in the US. I've seen a picture of it. It's a floor-mounted thing. It's white. It's got a curved top with the Mercedes emblem on it. Got to compete with Tesla. So, yes, sir. On these, none. Now they have energy management, they have thermal management in it. It's actually liquid cooled, has a built-in radiator and fans and circulation system, has its own built-in electronics. It's a very sophisticated device, actually. As far as I know, it's not through UL yet. Well, maybe a detail. UL's pretty tough on things like this. And, you know, is it a fire hazard? Do we know that? I mean, not only can it produce a fire, but what happens to it in a house fire? These kind of issues, I'm not sure, you know, I haven't really heard all the details on that as to how that's going to work. But I think, you know, I think it's pretty obvious we're going to be moving to on-site storage in houses. I mean, they're doing a lot more of it in Europe than they are here. So I think that is the future in it. And this is pretty groundbreaking. Yes, sir. If I remember correctly, I don't remember the exact weight, but I remember thinking 2 heavy guys are going to have a hard time putting it on the wall. And there's another question I actually had for the technician that I was talking to from Tesla, you know, because these are designed to either go in your garage or they could be outdoor mounted. They're weatherproof. But if it's going to be outdoor mounted, do they have some sort of theft prevention system, you know? They hadn't even thought of that. So, but that's an important thing, you know. I mean, 2 heavy guys in a van could come up to your house and steal your battery. Because it is going to be, you know, at that kind of voltage, it's a very lethal DC voltage. So all the, you know, it's going to be plug-in connectors. You know, it's not going to be something where you're manually wiring it up at 380 volts DC. It's going to all be plug and play, essentially. So theft prevention is something that they need to think about. 220 pounds, yeah, you know, I mean, it's manageable. You put a bracket up on the wall, 2 heavy guys can pick that up. It's, you know, yeah, exactly, you know, but yeah, it's heavy. And, you know, really, I mean, even if you say 10 kilowatt hours of storage, that's not a whole lot of energy storage. So their original literature said you could put as many as 9 of these together. They really only have the equipment to do 2 at this time. It requires communications gear that they haven't quite worked out. The release of this to the press was, in my opinion, somewhat premature. I think it was really there more to generate excitement and build up stock price than it is to actually offer something. The prices that they stated are their out-of-factory price. We might pay that as a distributor, although I bet that it's going to cost us more than that. But that's certainly not the price going out to the public, and yet that's what they told everyone it's going to be. It's going to be $3,000. Well, it isn't. It's also probably not going to be sold as just a standalone unit. It's going to be sold as a system. And that may be one of the ways they get it UL listed, because they can get it UL recognized as a component, but only with a complete system are they going to get it UL listed. So it's going to come with an inverter and connections and all that kind of stuff. And SolarEdge is working with them, Fronius is working with them. I think we're going to see virtually all the inverter manufacturers going to high voltage inverters at some point. But this is pretty groundbreaking. Yeah, pleasing design, decorative cover. I never particularly considered batteries sexy, but I guess these guys are pushing that right now. It says up here 2 to 3 times the price of lead acid batteries. Again, the pricing that they're giving us is preliminary, and it may even be more expensive than that. Still only has about a 10-year lifespan, so I don't see a huge technology there too. The interesting thing is another thing that's being thought of. You know, if every driveway had a 400-mile range electric car parked in it, that's an enormous distributed battery bank. Millions of batteries sitting in your driveway. There's no reason why that battery couldn't be connected to your car and provide some of the same benefits that what this does. There's actually a whole system being developed in Europe called vehicle to grid, where you have a smart grid thing where the utility company can actually tap into everyone's car. You know, when you're parked at work, you plug in the car, and it keeps tabs of energy in and out of the car. The utility can use that for peak load instead of having to run gas-fired peaker plants. And so they pay you. I mean, there's a monetary exchange for the energy that they take out of your battery. I would hope they don't drain you completely. I'm sure they have some sort of arrangements there. But, you know, that kind of smart grid, big scale thing is what we're going to see in the future. We're going to see a lot of stuff like that, which is, you know, pretty exciting technology. Lithium ion, you know, just like the Tesla, but just in, you know, more basic, not quite as sexy industrial design. Certainly out there, I mean, we've been working with a variety of companies producing lithium ion. We're not actually currently offering a product in this because we just don't see anything that's cost effective enough to really, you know, be a distributor for at stock and that kind of thing. It just hasn't quite taken off yet. Yeah. Yeah, we'll, you know, I'm sure we will. You know, we're keeping a pretty tight load on it and see where that goes. There's other technologies like nickel-based batteries. I think we're probably all familiar with the old NiCads, which weren't all that good really in the small cells. Cadmium is very toxic heavy metal, builds up in your body. It's very toxic material. So I'm not a fan of NiCad batteries, although they can be used in certain industrial applications. However, nickel iron and nickel metal hydride are very interesting technologies, particularly the nickel iron. Nickel iron's been around for years. Actually, Thomas Edison, that was his main battery thing, was nickel iron, and they were used extensively in the rural electrification projects in the 20s and 30s in the Midwest. There were many, many farms that had nickel iron battery banks that lasted for generations, and some of them are actually still working 80 years, 90 years later. Very long-lasting technology. Not real cheap. Again, 3 to 5 times the price of lead-acid batteries. They generally have very broad voltage ranges. They have to be charged up to fairly high voltages, and they drop to fairly low voltages. They have some issues. That's not such a big issue other than the fact that things like inverters and charge controllers aren't really designed for that kind of a spread. So you don't necessarily have the equipment to be able to use so much of it. It has a very flat voltage to the state of charge, and then it goes zip. So it doesn't give you much warning. You can't use voltage as really an indicator of state of charge. You have to have an amp hour meter, counting the amp hours going in or coming out of it. Yeah, less hazardous materials, not particularly true of NiCads. Again, cadmium is a very toxic material, very hard to recycle. But they can have amazing cycle life. I mean, it says here, you know, 11,000 cycles or more at 80% depth of discharge for flooded nickel iron batteries, which is kind of what these are down here, or something similar to that. There's a company called Iron Edison that's making them now. They're expensive. They're very long lasting. They're very forgiving of problems. They're an interesting technology. I think the price is probably going to keep them as kind of a niche market. I don't see their price coming down nearly as much as lithium or the sodium ion batteries. They still work quite well in flashlight cells. Nickel metal hydride rechargeable flashlight batteries are still quite good. You know, they're very robust, no sudden failures. One of the problems, you know, they are an alkaline battery instead of an acid electrolyte. It's an alkaline substance. And one problem that happens with these in flooded cell batteries is they get contaminated by the CO2 in the air. Carbon contaminates the electrolyte. So they very often need electrolyte flushes and changes periodically, like maybe every 8 to 10 years. Big hassle to do that, you know, but you know, the actual plates in the battery are not corroded or depleted through age, so it's really just the electrolyte, and it can be changed. Interesting technology too, sometimes worth looking into. It is a low cell voltage, 1.2 volts per cell. So in terms of, I'm going to talk mostly about lead acid because that's still really kind of the most common thing. Capacity is measured in ampere hours provided to the loads. That changes depending on how quickly you try to draw energy out of the battery. Typically, batteries are rated at a 20-hour rating, meaning that, say for instance, it's a 100 amp hour battery. If you were to discharge that battery at 5 amps, you would get 20 hours out of it to 100% discharge rate. Now, the thing about lead acid batteries is that last 20% is not very usable energy. So really, we only go to 80% in our calculations. It's kind of like with your flashlight. You know, you get to the point where you're using a flashlight where you can look at the bulb and you can see the bulb is lit, but you can't see where you're walking. You know, the battery's essentially dead. There's still energy in there, but it's not usable energy. So that's why we use that 80% factor. At 80% of a battery's capacity, that's usable energy, even though it's rated at the 100%. So again, a 100 amp hour battery can really only deliver 80 amp hours into your loads if you're going to do that. And the faster you try to draw the energy out of the battery, the less of a percentage of the capacity you're going to get. If you try to draw 100 at the 1 hour rate, again, a 100 amp hour battery would be 100 amps, you're only going to get about 59% of the rating of the battery. And what happens there, it's a chemical reaction reducing that electrical current, and the chemical reaction can only happen at a certain speed. And the faster you try to speed that up, the less efficient that process becomes, and that's why you get less output out of it. Lead acid batteries generally need to be cycled a few times before they actually work their way in and become full capacity. When they come from the factory, they don't really develop full capacity. They're a lot like muscles. They need to be exercised and worked before they're really working well. The hotter the temperature, the more self-discharge on a battery. And you can also see from this chart here that temperature, this is in Fahrenheit, centigrade on the right, affects the capacity of the battery. So at 0 degrees Fahrenheit, the battery only has about 50% of its rated capacity. So just be aware of that. If the battery is going to be in a really cold environment, that you have to oversize it based on the temperature things. I did a telecom site project years ago, northern Quebec province in Canada. It was a mountaintop telecom receiver site, and we had to oversize the batteries by a factor of 6 just because of the low temperature performance of the battery. There was no way to get propane up there for heaters or anything like that, so they were going to be operating very cold. And so, yeah, sometimes it makes for huge battery banks, but you have to do it. That's just what it does. Battery wiring, just like PV modules, you know, again, each cell is 2 volts. The battery itself might have 3 cells in it and be 6 volts, and you know, then you need to wire them in series and then in series parallel to get the proper output amperage and voltage. So, you know, if you put them in series, you're adding voltage. You put them in parallel connection, you're adding capacity or amp hour capacity. So obviously in series, you're connecting the positive of the first battery to the negative of the second battery and so on. For instance, 2 12-volt batteries rated at 220 amp hours will yield a 24-volt battery bank at 220 amp hours. So each battery has a certain amount of storage in it, and by putting them in series, you're increasing the voltage but not the amp hour capacity. But since voltage times amp hours is watt hours, every time you add a battery, you're adding more watt hours of storage. When you're putting them in parallel, it's additive. The capacity is additive, but the voltage remains the same. So in this case, if these were 12-volt batteries, they would stay at 12 volts, but you would have twice the amp hour capacity. So again, in my example here, 12-volt DC batteries, 220 amp hours each. You put them in parallel, you still have 12 volts, but now it's 440 amp hours of capacity. So so you can, by doing a combination of series and parallel strings, you can end up with higher voltage and higher capacity. Somewhat unlimited, although we do, and all the manufacturers will say that to not put more than 3 strings in parallel. You'll get the maximum life out of a lead acid battery if you just have one series string of batteries at the correct voltage and the correct amp hours for your system. And the reason for that is if you have one string, the electrical current to complete the circuit has to go through every battery evenly. So they all get charged and discharged very evenly, and they last the longest lifespan. As soon as you put two strings in parallel, you've got interconnections between them. You're introducing resistances and variations. Electricity is always going to take the path of least resistance. So if one string has slightly less resistance in it because of maybe a loose connection or a cable clamp or just manufacturing difference, more energy is going to either go in or come out of that string with the least resistance. The one with the higher resistance is going to get less charging current, less discharging current. They're going to get imbalances in there. You put two strings in parallel. If you keep them charged well, you equalize them often and whatnot, they last pretty good. I mean, you might, maybe you're losing 8–10% of its lifespan or something like that. As soon as you put three, you're really teetering on the edge there. You really have to pay attention to them. It's actually a good idea over time, like every 6 months, to move the batteries around within strings and between strings, just to try to keep them more even. No, hardly anybody except me does that. It's a maintenance thing. But when you get over 3 strings, it becomes almost impossible to keep everything evenly charged. Now, there are ways around this. Big, like telecommunications gears, big industrial applications will have, they have huge battery banks. There's just no way they can have 1 to 3 strings of batteries. What they do there is they'll have big, wall-mounted bus bars and run cables of exact equal length and resistance to every string to these central bus bars, and then draw off of that instead of daisy chaining the batteries. And that's still not perfect, but it's better, Excuse me? Yeah, yeah, it gets expensive. Yes, sir. Yeah. They don't have this problem. That's right. They're self-equalizing. Although he did say also that you can't, they don't recommend mixing new batteries with old ones because, every battery, from the day it's manufactured, it starts to age. And its impedance, its resistances will change over time. So if you had an older, say you had a 3-year-old or a 5-year-old Aquaman battery and you wanted to add another one, that's not recommended because they're not going to charge and discharge evenly because of an age factor. You could use, sure, but it would have to have different charging circuits, different inverters, different loads. It has to be whole separate systems at that point, but you could certainly do that. Yes? It doesn't, well, it depends on how you're doing it. It doesn't really matter, obviously you're running a positive and you're running a negative. Those two don't have to be equal lengths. If you had, say, 1 string of batteries, you could have a 5-foot negative and a 10-foot positive. It's still completing a single circuit, so there's really no difference there. Now, if you had multiple strings of batteries that are then, with separate cables going to an inverter or a separate bus bar, yeah, those should be the same because you're trying to equalize the draw from each string, But it's not within 1 string, or even if you daisy chain them together, say a parallel connection like this. And actually, there's a very important point here I want to point out on this. This is really important. Is that you have two 12-volt batteries here, right? They both have negative terminals, they both have positive terminals. It's very important to draw the negative off of one corner and the positive off the other. If you drew the negative off of this and the positive off of this one, this battery would get charged and discharged a lot. But because of the extra resistance in these cables, that one would be sitting there in the background. And you're going to get a huge imbalance in the charge and discharge cycle of those batteries. So it's the same kind of thing with cables of equal length. If you have parallel sets of batteries all connected to a single source, yes, those cables should all be the same. But if you have it all connected into one bank going to a single inverter, let's say, it doesn't matter if the positive and negative are different because you're doing a circuit. So it's just all the current has to go through that circuit. It's not really that important. It is important that these be the same. Here, you don't want, for instance, this is only 2, but let's say you had 3 of them. You don't want one to be short and one to be long because then you're going to end up with different resistances between the parallel sets. Yes, sir? Oh, yeah, they're like 3-tier rack, that, yeah. That's right, yeah, they do that because they go to that central bus bar that, you know, they go through a circuit breaker. You know, Outback has a AGM system for home battery backup that has either 2 or 3 shelves. Excuse me, and each shelf holds 4 12-volt batteries for 48 volts. You have up to 3 strings. And they internal wire that. Each string has its own circuit breaker, and they have all even-sized cables that then go up to a central plate, a copper plate, a plated plate. That's the central bus bar. So all of those need to be all equal length to have all equal resistances within the battery bank. But then the output of that doesn't have to be. You know, you could have the negative coming off that bus bar plate to the inverter shorter than the positive or vice versa. It's not going to matter because it's all producing a circuit. So I think, oh, yeah. Yeah, we ran over time already. I don't know, people who have other classes to go to, or yeah, I guess there's another class coming in, so I'll have to call it. So anyway, we are going to have this presentation available to all of you. I'm sorry I didn't get through the whole thing because I was going to explain battery backup systems, charging sources. Yeah. Thanks. Maybe we'll do 3 hours next year. And you're welcome to meet with me personally. I also have NAB certificates for people that need that.